Hello and welcome. In this video, we're going to explore two fundamental concepts in Python: lists and generators. We will understand their differences and see where each one shines. Lists are represented by square brackets. Generators are represented by an arrow within parentheses. Let's dive in. Let's begin by taking a closer look at lists. Lists in Python are defined by the following four characteristics. First, lists use eager evaluation, which means values are computed immediately. Second, lists store all their values in memory. Third, lists are indexable and mutable, meaning we can access elements by their position and change the list after it is created. And fourth, lists allow multiple iterations. You can loop through them as many times as needed. Here is an example. The code defines a function called createSquares that takes an integer n as input. Inside the function, a list named squares is initialized. A for loop iterates from I equals 0 to n minus 1. In each iteration, the square of I is calculated using I multiplied by I, and then appended to the squares list. Finally, the function returns the squares list. After calling the function createSquares with argument 5, the result is stored in a variable called numbers. When the numbers list is printed, it outputs 0, 1, 4, 9, 16, which are the squares of the numbers 0 through 4. Now let's turn our attention to generators. Generators in Python are defined by the following four characteristics. First, generators use lazy evaluation. This means values are computed only when they are needed. Second, values are generated one at a time, not all at once. Third, they are memory efficient, especially when dealing with large sequences. And fourth, generators support single-pass iteration. Once you've iterated through all the values, you can't start over from the beginning unless you create a new generator object. Here is an example. The code defines a generator function called createSquares that takes an integer n as input. Instead of storing the squares in a list, the yield keyword is used to produce each square one at a time. After calling the function createSquares with argument 5, the result is stored in a variable called numbers. When the numbers variable is printed, it outputs generator object, indicating that it does not immediately compute and store all the values, but it creates a generator object. After that, a for loop iterates through the numbers generator object and prints each number, which results in 0, 1, 4, 9, 16. These values are generated on demand as the loop progresses. Now let's compare the memory usage of lists and generators. On the left, we have a list. The code defines a function called createList that takes an integer n as input. Inside the function, a list named result is initialized. A for loop iterates from I equals 0 to n minus 1. In each iteration, the square of I is calculated using I multiplied by I, and then appended to the result list. Finally, the function returns the result list. After calling the function createList with argument 1,000,000, the result is stored in a variable called squares. For a list of 1,000,000 items, the memory usage is approximately 38 megabytes. On the right, we have a generator. The code defines a generator function called createGenerator that takes an integer n as input. The for loop iterates from I equals 0 to n minus 1. The yield keyword is used to produce each square one at a time. After calling the function createGenerator with argument 1,000,000, the result is stored in a variable called squares. The memory usage is about 104 bytes. You can see that generators are significantly more memory efficient than lists, especially for large sequences. Now let's compare generator expressions versus list comprehensions. On the left is list comprehension. The code creates a list of squares using list comprehension. For each x in the range 0 to 9, it calculates x multiplied by x and includes it in the list. The list is created immediately, and all the items are computed at once. When the squares list is printed, it outputs 0, 1, 4, 9, 16, 25, 36, 49, 64, 81. On the right, the code creates a generator expression that calculates the squares for each x in the range 0 to 9. In contrast to list comprehension, It only creates a generator object, not the actual list of squares. When the squares variable is printed, it outputs generator object. List comprehensions use eager evaluation, meaning all values are computed at once. List comprehensions can be indexed. Multiple iterations are possible. Generator expressions use lazy evaluation, meaning values are computed on demand. There is no indexing. It allows one-time iteration only. Generators can create infinite sequences without running into memory issues, which is something that lists cannot do. Because generators compute values on demand, you can take as many values as needed without generating the entire sequence. Trying to create an infinite sequence using a list would require infinite memory. The code defines a generator function called Fibonacci. It initializes two variables, a and b, to 0 and 1 respectively. It yields the current value of a, and then updates a and b to the next two numbers in the Fibonacci sequence. This process repeats indefinitely, generating an infinite sequence of Fibonacci numbers. The code gets the first 10 Fibonacci numbers by calling the Fibonacci generator function, storing it in a variable called fib. A for loop iterates 10 times and prints the next number generated by the Fibonacci generator. The output is 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. Generators can be chained together to create data processing pipelines, in which each generator transforms the data and passes it to the next generator in the chain. The diagram displays the pipeline. It starts with the generate step, then filters the data, and finally transforms the data. This is an example. The code defines a generator function called numbers. It generates numbers from 1 to 10 using a for loop and the yield keyword. Another generator function called even filter takes a sequence of numbers as input and yields only the even numbers in the sequence. A generator function called squared takes a sequence of numbers as input and yields the square of each number in the sequence. The code demonstrates chaining the generators together. First, the numbers generator is initialized, then the numbers generator is passed to the even filter generator. Finally, the even filter generator is passed to the squared generator. A for loop iterates through the squares generator and prints each of the squares, which are 4, 16, 36, 64, and 100. Let's take a look at a performance comparison of lists and generators. Here's a table summarizing the key differences. For creation time, lists are slower for large collections because they need to compute and store all values immediately. Generators, on the other hand, instantly create a generator object. For memory usage, lists store all items in memory, which can be inefficient for large datasets. Generators are more memory efficient because they only store the current item. For access time, lists offer O1, random access, meaning you can quickly access any element by its index. Generators only support sequential access, meaning you must iterate through the sequence to get to a specific element. For processing large data, lists may face memory constraints, as they need to load the entire dataset into memory. Generators stream data efficiently, making them suitable for processing large files or infinite sequences. For multiple iterations, lists support multiple iterations, allowing you to loop through the data as many times as needed. Generators only allow a single pass, so once you've iterated through all the values, you cannot start over. Remember to choose the right tool based on your specific use case and data size. So, when should you use lists and when should you use generators? Use lists when you need to access items multiple times, you need random access to elements, the dataset is small and fits in memory, you need to use list methods such as sort or append, and you need to modify the collection. Use generators when working with large datasets, creating data processing pipelines, representing infinite sequences. Memory efficiency is critical, and you only need to iterate once. Let's explore some real-world examples. First is processing large files. The code defines a generator function called processLargeFile that takes a file name as input. It opens the file in read mode, iterates through each line in the file and yields the line after removing leading and trailing whitespaces and converting it to uppercase. The code demonstrates how to process a 10 GB file efficiently. It iterates through each line in the process large file generator and prints the line if it contains the word error. This enables processing huge files line by line without loading the entire file into memory. Another example is data pipeline for web scraping. The code defines a generator function called fetchURLs that yields a list of URLs. A generator function called fetchData takes a list of URLs as input and yields the text content of the web page after sending a request to the URL. A generator function called parseData takes HTML data as input and yields the parsed HTML content using Beautiful Soup. The code chains the generators together. Pages is initialized with parseData, fetchData, and fetchURLs. Generator pipelines allow processing data in stages without intermediate storage, making web scraping efficient. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.